Differential equations, type 2, real world. C, acceleration. So in 1999, we have the rocket engine of a 12-ton missile. It produces a thrust of 180.1 kilonewtons. The missile is launched in a vertical direction, and the air resistance is v squared newtons, where v is the speed of the missile. And we have to first of all find the speed of the missile after 30 seconds. Okay, so let's have a look at what this looks like. So we have some sort of a rocket, okay, lovely diagram, right? But we have the rocket is launched into the air, and of course what is going to act on it? Well, it's going to have thrust driving it up, so the engines. It's going to have air resistance acting down on it as it's lifting up through the air. And of course then the weight of the rocket itself is going to be trying to pull it back down. So if we look at the values given to us in the question, what we can see is we have a mass is 12 tons. Now what is a ton? So in the old maths tables years ago they used to give you that. But you need to know that 1 ton is 1,000 kilograms, so 12 tons is 12,000 kilograms. We're also given the thrust of the engines. So the tractive force is 180.1, and that's kilonewtons. So I'm going to change that to 180,100 newtons. So kilo is 1,000. And of course then we also know the resistance of the air is given to us by v squared newtons. Okay. So if we're looking at our net forces acting in this diagram, then it is accelerating in an upward direction. So our leading force is going to be our tractive force, our thrust from the engines, and then our opposing forces is going to be our air resistance and our weight. So if we sub those values in, we have 180,100 for T, minus v squared, minus the weight. Well, the weight, remember, is mass times gravity. And therefore we have 12,000 G is equal to the mass, which is 12,000 times the acceleration. So of course if I get A on its own there, well, what do I end up with? Well, I end up with 180,100 minus 12,000 G minus V squared all over 12,000. And if I simplify that, that gives me 62,500 minus v squared over 12,000. Okay, so now I have my acceleration equation. I'm ready to start my integration. So I'm looking for the speed of the missile after 30 seconds. So velocity and time are going to be my start and end limits. So let's write up here, what have we got? A, we just said, was 62,500 minus v squared all over 12,000. So my start and end limits. With the start, my velocity is 0 and my time is 0. I'm looking for the change in velocity with respect to 30 seconds. So find the speed of the missile after 30 seconds. Okay, so we're looking for that change in velocity. So our acceleration then is going to be the rate of change of velocity with respect to time. And therefore, if I rearrange that to get my velocity on its own, I have 12,000 divided by 62,500 minus v squared. dv is equal to dt. And my upper limits are my end limits. and my lower limits are my start limits. So what we have here is something that's quite an unusual integral, because it's not a linear function, and it's also not going to be any of our inverse functions. So what I'm going to get to do is I'm going to take the 12,000 out here, so that you can see we're left with 1 over 62,500 minus v squared dv dt. So it's not 1 over a linear function, so it cannot be natural log. It's not 1 over something squared plus something squared, so it's not tan inverse. And it's not 1 over the square root of something squared minus something squared, so it's not sine inverse. So can I even write the denominator as something squared? Well, yes, I can, because 250 squared is 62,500. So what we actually have is a very unusual integral, and this can be found in page 26 of your maths tables. So it's rare that we would actually use this. And what you'll see is 1 over a squared minus x squared. And when we integrate that, we get 1 over 2a natural log of a plus x over a minus x. So it would have cut a lot of students out in that year. Okay, so let's move on to the next page so we can see what we're integrating. So let's just mark, this is going to be our a value and this is going to be our x value. So therefore, what does that give us? Well, it gives us 12,000 times, and we have 1 over 2 times a. Well, a we said was 250. Natural log of a, 250, plus x, which was v, over 250 minus v. And that's within the limits of v and 0. And when I integrate 1 with respect to t, I just get t within the limits of 30 and 0. So of course, if I simplify that 12,000 by 1 over 500, well, what do we end up with? So we have 24 natural log of 250 plus v, 250 minus v. And of course, that's within the limits of v and 0. And if I put in for my limits next, well, I'll end up with 24 natural log of 250 plus v, 250 minus v, and then minus 24 times natural log of 250 over 250, and that's equal to 30. And of course, natural log of 1 is 0. So all of that just goes to 0. So I need to get v on its own here now. So I have natural log of 250 plus v over 250 minus v. And if I divide 30 across by 24, I get 1.25. And we have to remember then that natural log is the same as log to the base e. So therefore, I can actually write this as 250 plus v over 250 minus v is equal to e to the power of 1.25. So if I rearrange that, that gives me 250 plus v is equal to 250 minus v times e to 1.25. So 250 plus v is equal to 250 e to the 1.25 minus v e to the power of 1.25. Bring all the v's to the left. So that gives me v plus v is equal to 250 minus 250. Take out v as being common. And then dividing across to get v on its own. And that gives me v is equal to 138.64, and that's meters per second. So a good bit of algebra just involved in tidying that up there, okay? All right, so the next part of the question, if we go back, says find the percentage error if there's no air resistance. So in other words, if we ignore air resistance, what's going to happen? So if we've no air resistance, we have to come back to this equation here. How is that going to affect our value? So let's have a look. So if we have F equals ma with no air resistance, well, that means that we're going to end up with T minus W equals ma. So our T was 180,100. So our weight was 12,000 G equals our mass, which is 12,000 A. So I can get A on its own there by dividing everything across by 12,000. And that gives me an acceleration of 5.2083 meters per second squared. So we have a value for A. So if I know what U is and the acceleration and the time, well, we have V, that final velocity, if we're looking at that change in time, will be equal to 0 plus A times the time. And therefore the velocity over that 30-second period will be 156.25 meters per second. So therefore, if we're looking for a percentage error, well, our percentage error is going to be the difference between the two over our actual value that we got. So our difference, well, we have 156.25 minus what we got there a second ago, which was 138.64 over our 138.64, gives us a percentage error then, times 100 of course, of 12.7%. Okay.